Hi, you guys. So today we're starting new material. We're getting more into calculus. We'll be doing a little bit more in the just-in-time text throughout the semester, but for the most part, we're now going to just be pulling out of the calculus textbook. So anytime I don't put, if we're doing just-in-time, I'll put like JIT before the section number, but if it's just the number, then it's out of the calculus textbook. Okay. All right, so calculus has three main ideas: limits, derivatives, and integrals. Okay, and so we'll start with limits first because everything else kind of builds on that. Derivatives build on limits, integrals build on derivatives. Okay, so we'll start with limits. All right, so we want to look at two types of change. Okay, as we get into our limit definitions. So we've got average velocity and instantaneous velocity. Okay. In order to define these, we're going to define two different lines. So a tangent line, if I've got some curve, and let's say I want to draw the line tangent to that point, it's going to be the line that just kind of intersects at that point. Okay. It doesn't have another point in that immediate vicinity on the graph. Okay. It could intersect somewhere up there, but we're not concerned about that. We're only concerned about this little area, and it's only going to intersect that point. Okay, the other kind of line, so that's a tangent line. A secant line, okay, if I've got a curve, a secant line is if I've got 2 points on the graph, and it's the line that goes through those. Okay, so we're going to define average velocity using our secant line and instantaneous velocity using our tangent line. Okay, so if we start with average velocity, so we can find the average velocity between 2 points or just 2 times. Let's say we've got some position function s of t, okay? And so we're going to find the average velocity between 2 times, t1 and t2. And we find this by finding the slope between those 2 points. Okay, so your average velocity is going to be the same as the slope of the secant line. Okay. So if we have some curve, and let's say here is our point t1, and s of t1 is our y value, and then we've got this point t2, and s of t2 is our y value. Okay, and so we want the slope of that line. So we can find that just using our regular slope formula. So we've got VAV or VAVG. That's just stands for the average velocity. We use the AVG because we use V for velocity, and so we have to specify whether we're talking about the average or the instantaneous. So the average velocity, we can also use the slope of the secant line. Okay, but it's going to be s of t2 minus s of t1 divided by t2 minus t1. Okay, just the same slope formula we've been using. All right, so that's our average velocity. So now we can do an example. So let's say I've got our function s of t there, and we want to find the average velocity over our time interval 1 to 2. Okay, and so what this means is that we're going to have t1 is our 1, t2 is going to be 2. So we find our average velocity by doing s of, why are we not writing? We're going to do it by finding s of 2 minus s of 1 over 2 minus 1. Okay, so plugging into our function, we get 8 minus 16 plus 10. Okay, all of that is the s of 2. Okay, and then that minus 1 minus 5 plus, or 1 minus 4 plus 5, all of that is s of 1. Okay, and all that divided by 2 minus 1. And so that comes out to be 2 minus 2 over 1, which is just 0. Okay, so what this means is that this means that over the time interval one to 2, the average velocity is 0. Or another way to think about that is that the velocities average to change. Okay. So, or the velocities average to 0 change. Okay. So there's average velocity. And so with average velocity, we need 2 points, right? Well, what if we only have 1 point? Okay, if we only have 1 point and we need to find the slope of our tangent line, then we can use limits to estimate it. Okay, so how we do this is we calculate several average velocities, so several slopes of secant lines over smaller and smaller time intervals. Okay, and then we look for a pattern. So if I draw this out, let's say we've got our curve there. And I want the instantaneous velocity at this point. Okay, so what I'm looking for is the slope of that tangent line. But I don't know enough information. All I know is this point. So what I can do is I can find, if I pick several points and find the slopes of the secant lines as I get closer and closer to my point, then you can see as our point gets closer, we're getting closer and closer to what we need. So we take the slope of several secant lines, or calculate several average velocities, and they give us closer and closer to our tangent line. Okay. So in this case, the limit of our average velocities is called our instantaneous velocity. Okay. Or the slope of that tangent line. All right, so one way we can see these patterns is to look at tables. So if we look at this table, we've got the position, s of t, of some object that's moving along a line at time t. Okay, so think of it as at some point that's just kind of moving along this line. So we want to determine the average velocities over the time intervals, 2 to 2.01, 2 to 2.001, 2 to 2.0001. Okay, and then make a conjecture about the value of the instantaneous velocity at t equals 2. So these time intervals are getting closer, they're getting smaller and smaller. Okay. So what we can do is, as we calculate the average velocities for each of these time intervals, okay, if we see that they're getting close to a specific number, then that's going to be our instantaneous velocity. Okay, so we'll do that. We'll first do 2.01, our largest time interval. So that's going to be s of 2.01 minus s of 2 over 2.01 minus 2. So that'll be 55.9584 minus 56 divided by 0.01, which would be negative 0.4 or negative 4.16. Okay, so then we can do our second largest interval. So that'd be 2 to 2.001. Okay, so it'll be s of 2.001 minus s of 2 over 2.001 minus 2. So that comes out to be 55.995984 minus 56 over 0.001, which is negative 4.016. Okay, and then our last time interval will be 2 to 2.0001, and that's going to be our smallest time interval that we're looking at. So s of 2.0001 minus s of 2 over 2.0001 minus 2. Okay, is going to be 55.99959984 minus 56 over 0.0001, which comes out to be negative 4.0016. Okay, so we found, using our table, we found the average velocities for our intervals. And so as our intervals are getting smaller, what do we notice about the numbers? Well, they're getting closer and closer to negative 4. Okay, so our conjecture, or the thing that we suspect, is that the slope of our tangent line, or our instantaneous velocity, is going to be negative 4. Okay. So with each of these, we were calculating the slope of a secant line as we got closer and closer to that tangent line. Okay, that's something limits let us do, or that's one way to think about limits. Okay. Tangent lines can have a slope of 0. So if we had just kind of if you see this, be aware. If you've got a graph that looks like this, it can have a slope of 0. So a line has a slope of 0 when it's a horizontal line. So generally, it'll be when you have a minimum or a maximum, that's when you'll get that tangent line with a slope of 0. Okay, but it is possible, so. All right, that's all for today. The rest of this week, we'll introduce limits some more, and then talk about different ways we can algebraically calculate limits. Okay, today was kind of an introduction with the theory. But if you've got questions, you can ask me in class or email me.